Good afternoon, everyone. Thank you very, very much for joining us today. Really, really grateful to end the series, the Acceleration Consortium's first annual speaker series on a very high note. I would like or a low note, maybe, perhaps. I'm very pleased to introduce Lee Cronin. Lee is a chemist. He is the Regis Professor of Chemistry at the University of Glasgow and the founder and CEO of Chemify. He is known for his approach to digitization of chemistry and developing high digital to chemical transformation, known as chemputing, which you'll hopefully be hearing on a little bit more in a minute, which turns code into reactions and molecules. He has also developed a new theory for evolution and selection called assembly theory, which aims to quantify and explain how selection can occur in chemistry before biology. Lee is exploring how chemical synthesis can compute and what is needed for the evolution of intelligence, as well as designing new type of computational systems that use information encoded in chemical reactions and molecules. So great pleasure that I introduced Lee for this talk this afternoon. Thank you.
Technology work. So I was actually looking through my slides, my 627. I went back to the last one, and luckily the content is clear. You know, some people the same talk. I gave a talk yesterday in Michigan, and the content is completely different. And mainly, I'm glad that Christine's here because I've put a load of formulation discovery stuff in. Because I really like her work, so I was like, yeah, let's talk about that. So I like robots. I like robots that, especially flying robots. This is a robot I bought when I was in Reykjavik. Luckily, the volcano was erupting, so I flew the robot there. It's always cool. Oh, my friend, you made it. How's it going? We just started, so no stress. And you're looking very handsome.
Yes, okay.
So that's good. So the problem with this robot is if I didn't fly it back safely, I would have lost the video. So I was really shitting my pants, right? And there were people going, "Are you flying a drone in a volcano?" I was like, "Oh, cool, yes. What are we talking about? Of course." But anyway, I'll try not to swear too much today. But I really love robots in the lab, and this is quite a big lab, and I'm an inorganic chemist, and it's quite amazing when you're wandering up the hill. You just hear this boom, and it's like you're at the seaside, but actually it's a big pot of molten silica. So you don't get much more inorganic chemistry than that. Now, I'm kind of excited to give this talk because it's 90 slides of pure. It's 90 slides. So don't worry if you don't follow the slides because I don't understand the content of them either. The point is to cover all the areas that you guys are interested in, from abstraction to materials discovery, formulation discovery, robotics and chemistry, building your own robots and blowing the robots up. And I want to cover it all. And so please forgive me for going too fast. I'm happy to answer questions. And I'm also happy to answer emails if they're appropriately short. Too long, I can't read them. So that's the hint if you want to email me about it. What I'm going to try and tell you about slowly, though, is the abstractions I think are required to build a universal chemical environment. I'm going to talk about universal compute, and it's not just a fancy word I made up to annoy people, although it does annoy some people. We'll do some organic synthesis. We'll do some materials discovery. We'll do some formulation discovery, and we'll look at portable robots at the end. So first of all, I want to talk about abstractions, and this is something that I've singularly been unable to kind of really explain for many years. I'm more of a computer scientist than a chemist, but I couldn't really get into computer science for reasons that I won't go into now. But I've always thought about trying to build universal systems that have reach. Now, what I mean by universality is quite simple, is that I want, if there's any new example of a thing found, I can incorporate it into my system without having to rebuild the system. It's a bit like the number system, right? Roman numerals are not universal because there's the largest Roman numeral. Our number system is universal. Our language is universal because we can build new words and we can express new concepts. It's kind of annoying if you're a French speaker because English loves to basically, you can hack around with English, just new words. And so I'm not saying that English is universal and French isn't, because I won't get out of the room alive, but I'm just wanting to make the point that language does interesting things with universality. So let me kind of try and explain how we can borrow this from computer science, right? And I think there's a very diverse audience here, and I'm very surprised there aren't some hardcore computer scientists here. Computer science is basically, if you start at the hardware and right down at the bottom, you've got devices and transistors, and in chemistry, it's atoms and bonds. And if you go up a level, you have gates and registers, in chemistry, reagents and solvent. And then computer science with microarchitectures and reaction hardware. And then you start to make the transition from hardware to software with an instruction set architecture in synthetic conditions. Process control, machine code, start to go up. Reaction procedures, assembly language, programming language, retrosynthetic analysis, chemical programming algorithm, and then at the top, an application design. You can wiggle some of these around. I made this slide when I gave a talk at the Solvay, and I was trying to really explain how you can go from the bottom to the top in these abstractions. And I want to convince the chemists they're already thinking abstractions anyway. When you draw a reaction, that reaction, when you're drawing those bonds, is an abstraction of what you find in reality of experiment. So why are abstractions here in chemistry important? Well, if one of the things that's really trivial, if you're a computer scientist, is the concept of a Turing machine. So if A can do X and B can emulate A doing X, then B can do X because A and B are equivalent. What I want to be able to do is do this in chemistry, because then universal chemical processes will be provably complete. And this is kind of, what am I trying to say? I'm trying to say, like, Alan and I have been collaborating for a while. We've just got a paper in. I'm not going to talk about, because I don't want to break any embargoes or anything, but we're delighted. But if I can do some chemistry in my lab that makes a molecule, and I email or even send the code to Alan's lab, he can then say, oh my God, this isn't just Lee Cronin's shit robot. He just takes the abstraction, knows how to compile it, and then runs it on his hardware because he has an interpreter. And so what we're trying to do is make sure those interpreters are universal, so they can be used out of the box. So that's kind of the first big point I want to make. Also for fun, it really annoys the computer scientists, it really annoys the chemists. So I think we're onto something here. This is an actual Turing machine built with a mini puter. And if you know what a Turing machine has a tape, and you have a transition, and basically what you can do is, using image recognition, is move solvent around and basically change the state of the tape. Super trivial. Now though, if you start to add in chemical operations, the pH and things like that, and see color changes, you can incorporate these things together. And I want you to think about, if you're sitting there thinking, my gosh, it's trivial, that's great. Because it should be trivial to make chemical processes universal. In fact, the reality is when you go and read a paper and you take the synthesis and you go in your lab and try and do it. So you've got three options. A, it works, as said in the paper. B, you have to scrabble around and work out what their solvents were and what the order addition was. Or C, it's just made up. How many times did it work? Or what frequency does it work first time? Almost zero. Now, if you've got someone's software or an app that you bought and you put it on your iPhone and it only worked 1 in 3 times, you would not use that app. So why is it acceptable that chemists, material scientists, formulators basically will accept that the literature is unreadable? It's not acceptable. So I want to change that. And I want to change it with you guys and a few others. Now, one of the other things I want to talk about is the space of chemistry. There's a nice little picture showing the assembly of Taxol, and Taxol is a natural product. The space of molecules it covers is huge. There's literally an infinite number of molecules you can imagine that are chemically allowable. Maybe even Anatol can tell us which ones they might even exist, and then we can go make. And then Alan can compute the transition states, and then we can go do. So that's the biggest space. This is physically allowed. Okay? And what I want to be able to do is, there is then a subset of those that's synthetically accessible. Not all physically allowed molecules are synthetically accessible. And there's good reasons for that. And what I'm trying to do in my lab, and with collaborators around the world, including here, is to try and make as many of the synthetically allowed molecules as computable. And what does computable mean? It means expressed in a format that will run in a universal robot to do chemistry. That's all it is. Computation is to chemistry what computation is to mathematics. So it's very simple, almost trivial, but quite important, I think. This is current automation. right? It's like there's not even a divot here. Of course, we like to do peptide synthesis, nucleic acid synthesis. We will think about sugar synthesis, but still it's a trivial amount of the chemical space that we need. And I would argue that we need to go from here to here. This is why, I guess I'm preaching to the choir. So when it comes to universal compute, it's not that technical. Basically, I needed an automatic machine that would add stuff, shake stuff, set fire to it, heat it, and stir it, right? And you just have to record these things. And so what we started to do is try and, by building lots of different examples of the hardware, so there's a digital gas manifold, a combinatorial engine here, the liquid backbone, a portable computer, a picture of a computer that was doing work during lockdown, a Schlenkline, a search engine, a purification system, and a mini-puter. And so we started to build this hardware, just kind of finding the edge cases, because I'd be like, we build this, does that work? No, okay, does this work? No, and add in and just keep working out what unit operations. And now I've talked a lot about our frustrations with vendor-based, hardware, and some pumps and valves too expensive. Why can't we do liquid-liquid separations? All these things that you take for granted that should happen, that just don't happen. So I always get into trouble. So in 2012, I'm just going to give you a little bit of history where this came from. I gave a TED talk where I put this video where I said, just to annoy all the organic chemists, and said, it'll be trivial to 3D print drugs, right? Just think about it for a second. They were like getting angry. You can't 3D print a drug. The atoms don't come out of a nozzle. And I'm like, dudes, live a little. Use a 3D printer to print a molecule. How could you do that? So I basically gave this talk, it got viewed 1 million by 1 million people. And then I went back to my lab and went, the good news, we're going to 3D print drugs. Bad news is I've kind of told everyone it's going to be trivial and we can do it in a few days. So we took a riprap 3D printer, we 3D printed this test tube out of polypropylene, and we then basically made ibuprofen. And again, the organic chemists went, this is trivial, it's insane, you're stupid, what are you doing? But we used the heat bed in the 3D printer, we used the shaker to agitate it, and each of these pumps was connected to a COM port. And this is when I started realizing STL code to produce the test tube, COM port with code saying, please add in these materials. And this is where the chemical programming language started to say, I can now program this properly. I don't have to rely on a student to tell me they did it. They didn't misread their notes. No disrespect to students, they're in a hurry, they're trying to do stuff. There's no standards in the lab to do that, right? You try and impose those standards, things go wrong for very good human reasons. There's nothing wrong with chemists doing chemistry, but why don't we take the monotonous aspects out and automate those? That was the idea. So then during that process, I realized that when I was trying to explain the abstraction really badly to friends and colleagues, they were like, we don't know what you're talking about. What do you mean? And I reasoned, I said, well, look, in chemistry, you only need to do 4 things. You need to set up the reaction, you need to do a workup, you need to do isolation, you need to purify. Do all those 4 things. For any molecule, you can make any molecule. Okay, any molecule. There isn't any exception. As long as it's physically allowed, we can go and ask a theoretician, go and ask a computational chemist, then think about the retrosynthesis. If these guys and girls say yes, then you should be able to automate it. And what I came up against was people telling me that it simply wasn't possible. Like particularly gatekeepers in synthetic chemistry. And I was like, why is it not possible? And I'm like, do you need some kind of magic Harry Potter wand when I'm doing this? What is physically disallowed? And what it came to is they didn't want to tell you their tacit knowledge. They didn't want to tell you the secret. They didn't want to tell you that when you're doing a Grignard reaction as an undergrad, and you put the magnesium filings in, you see all this bubbling, do not add the haloalkane because it's still drying, because it's wet as hell. Wait until it stops bubbling, because you will then have converted all the water, and then I'll add the damn reagent, and then it will work. It's a trick we play on all the undergrads, and I was there, impatient. Oh yeah, there's something happening, squirt, fail, no reaction, okay? So kind of the Chemputer was born. The Chemputer was born out of the idea to basically automate organic chemistry. Actually, I tell a lie. I had no intention of automating organic chemistry, but it couldn't care less. I wanted to build a search engine to crack the origin of life. And I wrote these grants, and I put it in, and everyone went, This is stupid. Who cares? Origin of life is impossible. You're not going to make a search engine. No. And I was like, how do I actually get money to build technology that people care about? So I'll make drugs, then fine, have some money. And actually, a lot of this technology is being used for origin of life stuff. And sadly, I couldn't include assembly theory in origin of life because it would have been a 2-hour seminar rather than a 1.5 hours. So along what the Chemputer does, it allows us to take this abstract idea of adding, taking chemical prose, translating it into a language, and then running the language on a machine. And it's called KDL. Version 2 is about to be released open. Version 3 is coming as well because it's fully Turing complete. It has basically all the logic is embedded in it. So I don't let people randomly add functions in Python or some other place. So you go to dependency hell. Okay, dependency hell is not Turing complete. It may feel Turing complete because you can write a script. It is not. Okay, and I don't like non-deterministic programming when I'm trying to do chemistry. This is a very old set of pictures, but this is really how you build a computer. I think that it's about time. I've been talking with colleagues, with Alan, with many people for years about making this easier to build. We're now at the point where it is relatively trivial to build one of these if you've got access to a 3D printer and you've got some mechanical engineering skills. And the boards that we've got here, we're basically going to do a whole run of these, so several thousand are going to be available to collaborators because they're the hardest thing. So we're working on it. We haven't been good enough in getting this stuff out there, but I don't really believe in the democratization of chemistry. My friend Martin Burke does, but I believe in not, before I democratize, I need to get everybody in chemistry on board. This is the same thing that this consortium is doing, what you guys are doing, trying to get people on board, people trained, understanding the benefits to create a network effect. Then we can go further. So it's about doing this in steps, I think. Anyway, what I want to do is show you an example of running a reaction. So this is our retro KDL. We put a smile string, otherwise it's not playing. I will approach the computer and press the button. There's something wrong with the medium. So basically, we run retrosynthesis on this, and then it spits out some code. I'll explain this all in a second. It then spits out the graph. So this is actually the graph of the robot you have, so it compiles to the right graph. And what I've just shown you there is the retro KDL we have is the robots will only allow you to disconnect the molecule if it's done the reaction before, and you have a blueprint. That's the first kind of little secret. No blueprint, no cigar, right? So one of the things where we go wrong in retrosynthesis is the chemists are so like, yeah, I'm going to do this reaction in a really smart way and introduce 2 chiral centers simultaneously. It will also, bake you a cake and send a letter to your mom, and you'll have this molecule. No. You basically make sure that each reaction is well declared and has a good potential for working. Spit out the code, spit out reagents, go to the robot, add reagents, add code, press play, should work. If it doesn't work, you have an inquisition, check what's gone on. This is a very sped up version. You're going to see the abstraction reaction. So really sped up, work up. I did this for a billionaire, so I had about 18 seconds, I figured. So it's a bit longer than 18 seconds. Isolation. And then the final step is purification by crystallization. When I first presented this, all the organic chemists in the UK went, this is rubbish. Because you only do crystallization. And I was like, dudes, it's not that rubbish. And they were like, it was kind of funny. And in the end, it self-cleans as well. This was kind of the first version of the Chemputer. And I liked it. So the first paper we published on this made Viagra, rufinamide, and nitol. So sex, anti-seizure, and sleeping drugs. What more could you need? But the point was, these were quite trivial reactions to do. 3 steps, well, 2 of them were 3 steps, and rufinamide was just 2 steps. Same robot, same configuration, add in the reagents, add in the code, get different molecules. And I think that takes a while to sink in. Because the chemists, again, take it for granted about how much you have to set up, what unit operations you do. So we kind of expanded this. I embedded one of my friends' reactions, Marty Burks. He loves microborylate chemistry, so I kind of embedded it in there. We did some diazoline chemistry. I'm going to do peptide synthesis, and I'll tell you a little bit about that. So the whole point, if it's universal, it should be able to do existing automatic chemistry, and then a bit more, okay? So let's do some robotic organic chemistry. This was the time of lockdown this happened, so I had 8 organic chemists. Had to go home, it was quite sad. But then I seized my chance and said, okay, all right, we're at home, but why don't we just go to the literature and see what KDLs we can write? And let's pick the top 100 molecules that will shock and impress other organic chemists that you really can do chemistry robotically. And they did that. And then I convinced the university to give us the robots were socially distanced, right? I think photographs of them said there's no COVID in the robots, right? And then they were like, no. So I kind of said, okay, we'll make some antivirals. They went, okay, here's your certificate, and you go. And we did. The KDLs are out there. We did other stuff more interesting, but I think it was kind of cool. So we did a whole load of chemistry that covered these classes of chemistry. And I'm really proud of the team because, you know, this is all the chemistry they got to work on the robot. And they went in, the robots were socially distanced, they did each reaction 3 times. And guess what were the yields? Were the yields A, the same as literature, B, higher than literature, or C, lower than literature? You reckon higher? I would want them to be higher. They were lower. And they were consistently lower. And I was like, what on earth's going on? There's something a bit tricky going on. So I said, our robots are dumb. The organic chemists are the best. The manual chemists are the best ever. And they are the best, right, still, joking aside. But then I got the chemists, we came in and did them all by hand, and they were the same. What was happening in the literature, I think it was Corey, or maybe Woodward, said, when you do a reaction, you do it 3 times. And when you report the yield, do you report the highest, the lowest, or the standard deviation? Or the average, whatever you want. He told the entire world to report the highest because we have a duty to show the potential of the chemical reaction. So basically, he was invoking fraud on scale, and that's what graduate students have been doing ever since, because they have to get their yields better. I love a low yield if it's reproducible, right? More than a high yield. If I know, if I spend 12 hours of my life doing that reaction, and I will get that, you know, measly 50% yield, I'll take it over a line every time. Kind of funny. But this is a tribute to the team because the paper got into Science. It was great. You know, it went through. It was kind of like we turned a horror story into a. It was quite good. We engaged the community. We've now got 2 million digitally validated KDLs, 100,000 possible, done 50,000 chemical steps, 80,000 unit operations. The things have been running for 20,000 hours, and no explosions until 2 weeks ago. 2 explosions in the last year. One I paid for, and one I didn't plan for. I'll tell you about that in a minute. And so, I'm sorry about this. This point is very sensitive, and I'm very nervous, so I tend to push the plunge there too much. This is just showing how we can do automatic purification. It doesn't it won't be any shock to you if you've got an automatic robot or KDL. You can put on all the automatic kind of solutions for flash chromatography and run them, and they'll be just fine. So here's the idea. You've got your synthesis procedure in prose. You translate it to KDL. You do the reaction. You get the analytical chemistry. You validate the procedure, put it in a database, and then you can version it. And then someone like, you know, someone from Alan's group go, Lee did that reaction. He's used wrong catalyst. We'll use the right catalyst, get a better yield, better version, put it in the database. So you can have this kind of way of interacting with each other and collaborating. And I can see a time where we will be not trading to publish in Science and Nature, as great as that is, but publishing in a database and getting the most downloads. And like Alan and I don't know, I hope you don't mind me revealing our secret that we're going to compete for downloads. That's the idea. So we can also do microwave photochemistry and electrochemistry. There's an example here where we've got a microwave dongle. It's coated in silver foil because that's the Faraday cage. You don't go near the fume hood. I do not want to radiate you. But that's the microwave emitter. And we've been able to do quite a lot of library chemistry using this. So it's kind of cool because we can do massively parallel synthesis at the gram scale with microwaves accelerating things. Yes, we can do electrochemistry. Yes, we can do photochemistry, but everybody can do photochemistry, and I'm bored. If I see another photochemistry paper in Science or Nature or JAXA or Agavanta that tells me I do photochemistry, I'm going to put rusty nails in my eyes. No offense if you're doing photochemistry. We're doing it too. But it's kind of interesting. So skipping on. So hazardous chemistry. So I made a joke about this. My team said, look, if the computer is really going to be... Okay, I won't walk over there. If the computer is really going to be come into its own, why don't we really push the limits and see if we can do chemistry that you wouldn't normally want to do by hand? So we want to validate it, and we also want to do quite a lot of interesting chemistry. Can you do beauty chemistry? Yes, we've been doing it routinely. Can you do ozonolysis? Yes, methylations and azide chemistry. I would not do azide chemistry by hand anymore. Why would you? You don't have to lose an eye, as one Nobel Prize would have had. Just stopping the reaction. I would not give an eye for a Nobel Prize. Sorry. I would happily blow up a robot there. So the idea is to kind of reduce the risk to the researcher, have online sensor feedback, apply for failure detection, apply by-wire analysis, and basically see if we can get the whole thing to fail to safety and quench dangerous reactions. So there's a system here I'm going to show you where we did some an LDA reaction. It's frozen. Is it frozen? Okay. So we've got some video cameras, and we can basically look at the movement of the pumps and valves, and you can see here. I'm sorry. Do that again. No. Start video. And what you can see is the color change here as we're adding the reagent, and there's a quencher, so we can make sure that we can see the reaction is fully done and everything is safe, and there's no pyrophoric material left in the valves. And this is working really quite nicely. What we also decided to do is, if someone said, "Can we blow up a computer?" I was like, "No," and they're like, "Go on." I was like, "We're not blowing up a robot, we'll get told off." But my postdocs are very industrious, and they found a facility where we could go and put some plastic explosives in one. So here's plastic explosive around the detonator, here's the computer. There you go. So that's quite a lot. That's a few grams of plastic explosive. It was well contained. The thing is, we're never ever going to have that amount of explosive power in the lab. It's impossible to put it in there, or I mean, in our lab anyway. And it's quite nice to see the secondary containment work really well. Very interesting. A few weeks later, we were playing with some phosgene, and the backbone wasn't set up correctly, so we should have had. Basically, because the exotherm and one of the syringes exploded. It was a little bitty explosion, but nevertheless, it was contained within the device. We reprogrammed the graph, we made sure the phosgene didn't come into contact with the wrong solvent and cause an exotherm, so it's all safe, but it's really good to make sure that we kind of understand that, you know, the graph reading software, we should be able to say, okay, I've got an oxidant here and a reductant here, I'm not going to mix them with the valve head. That's a really bad idea. Make sure they're going into the flask. So there's all this kind of conditional logic you can do as a function of the materials. I know I haven't got that much time, but this pointer's going mad. So the next thing I think I'm going to stop using the pointer and let's use. So the next thing we were doing is, now we've got KDL, we're making KDL dynamic. I want to see if we can do optimization chemistry. Optimization in line. So we basically wired in all these sensors. So benchtop NMR is one of my favorites. Liquid sensor, HPLC, Raman spectroscopy, infrared spectroscopy, conductivity, and so on. So now we can start to do KDLs, and rather than being like fixed, it could say, you know, add reagent until exotherm, then stop, or add reagent until color changes, then do X. So you can have these conditions you can wire in, and we're doing this as a matter of course now, and then optimizing to make sure the KDL is right to get the right kinetics. A couple of examples here for adding materials. We're looking at liquid detection, Then this is looking for an exotherm here, looking at discolorization here for iodine addition to this iodination. So can we expand the chemistry beyond just normal organic chemistry? With this example here, how we built solid phase peptide synthesizer. Why on earth would you do this? I hear you think. Well, these robots cost about 100 grand. This costs 10. Sure, if I market it and sell it to you, I suppose I could sell it for quite a lot. But the point is, if you're building these things in the lab and you're trying to try out new workflows, this is quite nice because you can combine quite intricate peptide chemistry with other organic chemistry that you've got in your repertoire expressed in KDL. And the KDL is expressed in here for these blueprints. You've got the reagent specification, the executable script here. It's all totally compatible. So you can literally just say, you know, literally the KDL instruction will be just to draw in, to type in the peptide sequence and add it to the machine, and it just makes it. Same with RNA, same with some very basic sugars, but they are not as easy. So this is an example where we've done quite complex peptides. We're very close to completing human insulin in glass with all the correct folds through the oxidation chemistry. And this was just a campaign in adding the right oxidant at the right time, and then doing a lot of diligence to make sure that one was identical to human insulin that would be made in your pancreas. Made in glass, kind of proud about that. I thought it'd be $1 billion KDL, but no. You can do it more cheaply, probably, in these bioreactors. But nevertheless, it shows that you can do bio-level engineering. We can also do organocatalysis. This is an example here where we're basically installing chiral centers, where you do this organometallic protection step, and all these procedures are now blueprinted out. So you have the Grignard procedure here, the deprotection here, the silylation, and you can go around in loops and do several weeks worth of chemistry just in a few hours. So I think this is kind of showing how you can expand quite nicely. Now, how am I doing for time? I'm not doing that bad.
340, so.
Yeah, so I'll slow down. So now we'll go on to discovery. Of course, I want to use, so I'm not a big, probably you don't know, unless you follow my ridiculous Twitter feeds. I'm not really a big fan of AI, per se. I'm a fan of AI for curve fitting, because that's what it is, majority of it. But I am a fan of using good techniques for discovering new molecules. Now, the reason I don't like AI for discovery is one reason, and one reason though is I don't think inductivism can give you discoveries. And if you think it can do that, you need to read Karl Popper and understand what a discovery is. And I'll leave that there because this is not a philosophy seminar, and I could be quite wrong. What you can do, though, is generate new ideas and new designs quite well with generative AI. You can have a property model. And then the thing that I really like is this fact that right now, you can use the AI to basically postulate these crazy molecules, but you can never make them. So the poor synthetic chemist is like, what did you do? But you're like, please make this molecule, it's gonna cure this disease. So what I realized is one of the things you need to do is once you've taught your robot to do a minimum amount of organic chemistry, and you then encode that, you then explicitly whitelist those reactions. Now you say, okay, I want you to find me the perfect molecule that adheres to these properties, structural and so on, but I need it to be makeable using these reactions alone, thereby prioritizing synthesizability and testability so you can do active learning. And that AI, application of AI, I think is absolutely brilliant. Because active learning allows you to embody your discovery in the real world, in a real thing, make it, test it, and make your computational model better. And this is what I think a lot of people here are really excited and doing and trying to do in various ways. So what we did originally is this was pre-Chemputer in my lab. I mean, look at this mess. Right, this is, they were like, we're going to build this discovery machine and we're just going to wire it up and just run it. And the idea was, we have a whole bunch of reagents and we're going to discover a new reaction. And what is the best way to discover a new reaction? Well, the best way to discover a new reaction is to basically blindfold the student, take them to the reagent cupboard, make them pick 10 reagents at random, take the reagents out, take a gram of each, put them in the pots, and mix them together randomly and look for change. I guarantee that's the best way to do reaction discovery. Okay. Now, obviously, the safety officer wasn't wild about that idea. So we did kind of do a little bit of check. The student didn't know, didn't want to induce bias, but the safety officer kind of checked, so we weren't blowing up on that. And then the idea was basically have an NMR machine and an MS and just look for change, look for different things. And here, what you can do, it's really quite simple. You have those 10 reagents. Now, you could do one of two things. You could just say they're blinded. I don't care what they are. I'm just going to do the NMR of them at the beginning and look for change. Or I'm going to basically look at what chemistry could be possible from the Reaccess database or similar, and there will be my known knowns, and then look for known unknowns and unknown unknowns. Okay, and it'd be quite possible to do that. What we did during this is we developed a system. This is slightly out of date now, but we built a very rudimentary neural network for discriminating reactivity. It's better than support vector machine. And what's it showing? We were able to train the system to look for the most reactive combinations in the NMR and just produce NMR, which just produce samples. And the NMR was integrated in the search space, and that was okay. You basically, yeah, I won't go over too much here. We were able to generate new chemistry with that. But we wanted to kind of bring the chemputer idea together. So now we rebuilt it in terms of the chemputer. We expressed everything in KDL. This allows you to do design of experiments and generate loops and do things asynchronously. And so you can then really start to explore chemical space. And what we did here is use the Bayesian process to explore chemical reactivity and then try to basically discover these things. The way this will work, and this is super important, the algorithm discovers nothing, right? It doesn't discover anything. The human being using the algorithm discovers something. And I don't know why in AI right now, everyone looking at generative AI and ChatGPT thinks that they can discover stuff. It can't. It can give you new suggestions, and it can explain to you that you don't have adequate knowledge of the literature, which I don't, and I'm very happy for that. And I think that's where there's some very promising work. But it doesn't generate anything new. Okay, it does not. Well, sorry, no, it does generate new, it doesn't generate novelty. New is possible, novelty is not. So what we tried to do here is build a platform, a robotic platform that had this kind of Bayesian oracle together with with an expert chemist to basically go through this space and find new chemical reactions. And this is published in PNAS a year or two ago, so I won't explain this, and I'm sorry for the dead slide. But the bottom line here is when the system was running, and the postdoc, when I was negotiating with the postdoc to do this chemistry, he just said, please, can we actually have some interesting reagents? I don't want to spend 1,000 years with my postdoc. I love working here, but I'd like to get out in a couple of years. And I was like, all right. So what we did is we put in reagents that were likely to produce interesting reactions. We didn't tell the robot or the algorithm anything, and basically rediscovered all this chemistry. Okay, the Sonic Shira, Suzuki, Heck, Corner. So basically discovered just by trundling through this space, not fiddling with the stoichiometries too much, not fiddling the conditions too much, just mixing, heating, sampling, and it was able to kind of produce some quite good results. And yes, we're using this right now to discover reactions that were not that you haven't yet expected, right? That you wouldn't anticipate. So that's kind of one discovery part. The other thing I wanted to do, very much inspired by discussions that I had actually years ago with you, Anatol, right? You remember talking about this, where I said, could we train a model to turn noise into an electron density? And so what we did is we basically taught a machine learning model how to generate electron densities, and then we see, can we use the model to invent new molecules, and can these molecules be useful for anything? And what we did is we set up this workflow using QM9 database, basically went through a whole bunch of different processes that you can see here, where we made this electron density to SMILES translator model. We then decorated the electron density with electrostatic potentials and then translated it into SMILES. So the basic idea was like this. Can I take an active site, pour in some noise, turn that noise into electron density, turn it into a SMILE, and then basically then make that molecule, or buy that molecule and test it, check it combined. And what it did is it minimized the steric hindrance and maximized the ECPs. And it worked pretty well. These are the two guests, two hosts that we focused on, and we generated a whole load of new guests, and they bound. They weren't brilliant. This work took ages, so by the time I published it, everyone went, meh, it's already been done, 1,000 times. It hasn't already been done. It came out a few weeks ago, but it's kind of annoying working in areas that are quite hot where there's people doing derivative stuff. I wasn't really adequately able to explain because, it's like, so what? What I really wanted to do is have some proteins and make some new ligands and show they would bind and make them in the Chemputer. But, I prioritized the postdoc's need for a job, which you got, over my need for a random paper in a high impact journal, but you get the idea. So one of the things that we were kind of trying to say at the end is like, hopefully computing will increase discoverable chemistry because we get establish the design, generate the code, execute the code, and then use these two things and fuse them together. And basically we will be able to rapidly go around chemical space and go from kind of a protein target to a molecule in a matter of hours. It doesn't seem that complicated now, right? Yes, we'll need some GPUs. Yes, we'll need some robots. Yes, we'll need some happy organic chemists and a decent biochemical assay. But you can imagine putting those together for a few $1 million. So what I'm going to do now is move on to materials. So the loop that we want to go around is this idea of having experimental design, setting up a target, execute in the Chemputer, do analysis and update. And the example I wanted to show you in a moment is a nanomaterial system. Before I go there, I wanted to show you this kind of technology we've been developing in-house, similarly to the way that we build the Chemputer modules. We wanted to build a really, this is a monster. The student who built this just wouldn't stop. It's like, dude, can you please stop building the robots now? It's like, no, we just need this bit. We need, you see, we've got 2 wheels for synthesis, heating rig, spectroscopy rig, in the atmosphere, spectroscopy station. So these were all put together in this rig here, but they were all run using Kaidio again. So you could actually run this on a Chemputer, but it'd be really slow. It'd be like 1 nanoparticle reaction per massive round flask, whereas here you could run lots of simultaneous parallel reactions. And we also then built in the parallel Kaidio control, and this just shows you some of the parallel execution that we've got testing in the blueprints. So the basic idea was to say, okay, can I evolve a nanoparticle and can I make the material reliably and come up with a digital fingerprint for the molecule? And so the idea is to do seed-mediated gold and nanoparticle synthesis. The modular platform has liquid handling, temperature control, vessel transfer, and UV visible catalysis. And the whole idea is to literally have a kind of a dual process where we are dreaming up the type of shaped nanoparticle we want using a physical model, and then also looking, so basically actually in a model, a simulation, generating nanoparticles, and then generating the theoretical spectra, and then actually reducing them, and then looking at the actual spectra, and then looking at the difference between the two. And that's the idea. And so the way we did this is with a bunch of map elites. And then this is kind of where we have an exploration algorithm that allows you to sample. Then you give them a class index, and then you can basically go through the chemical space. And the elites with the highest fitness will regard as the parents, and you just keep mutating and going around. To cut a long story short, we were able to basically go through these levels, okay, from 4 different levels of seed-mediated reduction. And make a whole range of different particles. And what you can see in the results, pretty good optimization before and after. And then as we went through, we could basically have this hierarchical growth of rods, spheres, and then facet them further and fit very well with the spectroscopic data. All in kind of a closed loop, as it were. But it wasn't as entirely closed loop as we wanted because you have to do TM. And this is just too expensive, right? The UV is a really good proxy. So one question I have for this crowd, if you're into SDLs, self-driving labs and closed loop systems, is the trick is to have a really good proxy for your outcome. And I might say, why do you care if it's closed loop? I think closed loop is very expensive. And there's no shame in a human being touching their robot and doing something to it. It's very cheap, and you just need to make sure you automate the things that are the most annoying. And because we were trying to automate centrifugation, and it was just, hey, why did you do that? So I don't think closed loop is as important as we sometimes think. So I just want to throw it out there as a suggestion. I mean, if I had infinite money, sure. So anyway, we've got a whole bunch of different new nanoparticles found. The nice thing about this, though, is because we use KDL at the end, the code that came out we could reuse again and again, and we can give people a fingerprint. So you've got the UV vis fingerprint, you just run the reaction, you check the fingerprint is correct, you know in that solution you've got those particles. So we have basically a graph-based process for doing that. And this is a summary of all of it. So let's go on the formulation. This is where I actually started my origin of life stuff. And this is like the last few moments of the talk. So I know it's been a long talk. What I wanted to do is build a closed loop system for formulation. And the robot design here has a series of injectors, filling surfactant, water, acetone, waste. The acetone is cleaning, and you have a syringe cleaner, you have an arena, and the oil wheel. And the idea is to basically, our formulations are going to be embodied as oil droplets, right? And again, I got lots of anger from this. Lots of formulation chemists hate oil droplets. I'm like, they're cool, I can video them, I can get the physics from them, I get the elasticity, everything. Don't knock the oil droplet. So the reason is I want to build an evolutionary engine. And the idea is to kind of generate the droplet, which is like a cell, okay? And the cells will then go in my Darwinian arena, where I become a droplet fascist, droplet world. And then I would decide, for some arbitrary reason, which droplets would live, I would retain the formulation for, and which ones would die according to a problem. And that was kind of the idea. And so the robot is shown up here. You can see the two wheels of Geneva wheel. Just taking the formulation, putting them into the dish, and then the dish being rotated into the sample chamber, and then the experiment being done. And then at the end, you then rotate out, and you can see here the dish is automatically cleaned and dried. And there's these drying units here to just dry them. You just keep them around. And this is truly a closed loop formulation discovery system. It was mesmerizing to watch. And they do all sorts of weird shit, these droplets. Like, we just in plan for, they explode, they just do all sorts of things. So it's quite a lot of fun. So this is what kind of, we published this years ago now, but it's one of my favorite systems because it's the first closed loop self-driving system, and it was a whole bunch of fun to watch. We were able to do Darwinian evolution, so we were able to optimize the division, the motility, and the vibration. And just like in Darwinian evolution, you see fitness landscapes developed, and you could basically look at the genes, or these are the formulation components, go through the space defined by the environment. We also got funkier, you know, we could start to develop all sorts of kind of, now this thing is, we can put a state machine on here, oops. And we are basically building droplets that have very sophisticated behaviors. Sorry, I'll just go back so you can see that. And these are driven by a magnet. We can also put on high-speed video. The Raspberry Pi high-speed video camera is amazing. It can do 150 frames a second. They well overspec that, didn't they, for the price? So thank you very much, Raspberry Pi. And I don't think this video is working either, but let's see. I think my computer is just tired. There we go. So you can see this clearly slow motion, but look at the clarity. It's amazing. And you can look at deformation. And then what you can do is you can fit physics equations to it and deduce the mechanical properties, the elasticity, and all this from there. And then, okay, now you've got the actual experiments. You can generate theory, have a basic model. Really doesn't like me today. Working at all. So these movies up here were basically simulations of the droplets with very similar behavior, and just showing how we could actually build a pretty good computational model of these droplets. Now we're looking at them as dissipated structures because we're trying to build droplets of agency, and then we're basically making, graphing their behaviors to make this look at the emergence of information. Ooh. Okay, final part of the talk. It basically explain what an idiot I can be when I'm designing stuff. So since 2012 and 2022, we've been doing lots of 3D printing, making reactionware. And reactionware was the concept of basically taking your process chemistry and 3D printing the reactors so you could basically move chemistry within these reactors with minimal kind of kit, as shown here, right? So you could basically have some reaction chemistry going on in here, and then basically go, whoops. All this worked perfectly earlier. Sorry about this. Right.
It's true, I saw it.
Yes. So we can do the version of PowerPoint. We can also, with this portable system, we can also fingerprint the reaction and know it worked by the pressure. So what happens is you do all the chemistry, you add all the reagents, and you measure the difference in pressure. And if it gets clogged, the pressure changes, and you get a fingerprint. And that fingerprint at the end, and we did this for RNA synthesis, peptide synthesis, and 8 different drugs. And we were able to show that you could, if the pressure sensors, if the fingerprint is right, the reaction can, you know the reaction's worked. And so we did a lot of work characterizing the materials, and it's really nice proxy for basically knowing for sure that you've got analytical grade material coming out. Because we want to have a portable robot. Now, what's embarrassment about this? Well, we went to all this 3D printing for years. I was adamant we need to use 3D printing, and that was great. And the 3D printers are really annoying because they would break, and polypropylene is difficult to print with, and so PTFE. And then I realized one day that actually, if you think about it and you do the math, this is the minimal units, like Turing machine for it. You only need 2 filter bricks and 1 reactor connected in this configuration. You could get all of those, and you could, the subgraphs would all fit into that graph. I was like, oh, but then we went to glass, and that's cool because then you don't have all the problems associated with, with 3D printing all the time and getting all the plastic. And so we have this concept of this device, this portable unit. It actually has the logo of my company on here, Chemputation. And it's actually quite easy to build. Student building it over a period of about a day. As you can see the weather outside changing. And this is the actual robot here. It can do everything a computer can do, including all the workups. Runs on PyDL. It's making a brain cancer drug here, actually. And it just goes to show how easy it is with these tricons as well, but we can make it cheaper by using our own pumps. Costs less than 10K. And that's kind of awesome. So I guess I'm at the end now, and I'm sorry that there was so much information here. I'm very happy to share slides with you if you're interested, confidentially. Very happy to answer questions. But there is an important thing I want to say by covering all of this all in one go, is the philosophy is about rigorously encoding your experiments. That allows you to design experiments in new ways. It allows you to communicate with people much more clearly. And then in chemistry, you need a programming language for all these reasons, right? So the most thing I love is this idea of publication of executable chemical code, right? Because in the end, we're going to stop this tyranny of random papers and random journals lying about the yields. You're like, you made this molecule, think is that good? Show me the data. Give me the code and I'll make it on my machine. And so that's what I want to happen. And I think you guys want that to happen. Hopefully together we can make that happen. So this is kind of the summary. I haven't talked anything about the amazing collaboration I've had with Alan's team on the Madness collaboration. But when I talk to you guys next, I'm sure there'll be a next time. I will discuss that in detail. And one thing I want to be able to do is kind of Also, enable other researchers to build this rig. This one was designed and built in Glasgow 2 weeks. You've got amazing facilities being built here. You have existing facilities here to do this type of stuff. I very much encourage you to get together, start hacking together robots, thinking in a systems way, and having fun doing it. I want to acknowledge my funders, my team. This is how we release stress. If you watch carefully, this student's had enough. It's like, fuck it. Oh, there's more. This is during lockdown, right? We were like, how can we draw the graph better? Can we just use Oculus? So he's got his bowling ball now. But this is to simplify the frustration, right? Because building these robots, doing the coding is not easy. Okay, so I take my hat off. I take my hat off to all of you who are doing this. Yeah, he has to have some fun. Anyway, thank you very much for listening.